Okay, let's get started. And I kind of collect several problems that for the illustration of the last time. And let's get started. And I'm still working on it. So that's the 2412. And so let's start from this problem. So this is the problem last time we're still going to review it. So let's do a quick review on last time. Last time it's just, first we do the arithmetic sequence and the theory. And the sequence is just, it's the formula is that an equals to a1 plus n minus 1d. And then Sn basically is equal to n is the number of the elements, and multiply average of the head and the tail number divided by 2. So that's the formula. And if you plug in the n number, it will produce another thing. Then there's no infinite theory with arithmetic, because infinite theory usually always goes to infinity or negative infinity. Then we have geometric base. So this we actually get the sum by like reverse in the double sum. So in case you forget what's going on, then you can actually get it back. Then geometrics sequence and the theory, basically, an is actually equal to a1 multiply m multiply r to the n minus 1's power. And so basically this is the common ratio. And the geometric, there's a limit sum and unlimited sum. And limit sum is that basically we use the scale and the depth. So basically, because you scale and depth, I know that the next one basically is r multiply if you sum it up. So basically s n will be equal to basically you have to scale them up. So when you scale up, so basically you just minus 1 minus r. So the denominator is something that, then on the top is the first number will not disappear, basically is actually an actually a1 actually minus, basically it's actually minus a n plus 1. Basically this is what it is. And because you have to scale, basically when you sum it up, n equal to 1 to n, basically it's n is actually, so an is actually, this is n minus 1. So an plus 1 basically is a1 minus a1 multiply r to the n's. So 1 minus r. So this is just, you can also, like a1, you can extract out 1 minus r to the n's and over 1 minus r. So this is the finite sum. Then infinite sum, basically, the absolute value of r need to be less than 1. With this in mind, basically, infinite sum s will just be equal to a1 divided by 1 minus r. This term will go really small. So that's the way to solve those problems. And I think, to master the number, you know, like sequence and the series. First, you know, I encourage you to really write out the formula like this. I don't remember the formula. I just understand the mechanism of the, you know, how it works. So basically, I can write out freehand, without really, you know, try to memorize it. It's just, you know, it's based on it's a common difference, and the space between 1 and n is n minus 1. So basically, this will come naturally, and this is just, you know, reverse and average. And so this is just a common ratio. Then it's just scale and difference. Then this is just special case when it goes to infinity. And so basically, you know, that's the way that you can handle it. Okay, so let's do the problems that. So insert 3 arithmetic mean between 3 and 4. So basically, you know, if we understand this formula, so basically the first term is actually 3. So basically A1 equals 3. And 3 arithmetic mean, basically we have to insert 3 value. So basically it's going to be A. So it's 3. A1 is equal to 3. A2 going to be like, so there are 3 of them. A2 will be like 3 plus D. And A3 going to be 3 plus 2D, and A4 equal to 3 plus 3D. And so then A5 is actually equal, so A1 equal to 1, A5 equal to 4, also equal to 3 plus 4D. So basically, you know, if you understand the structure, data structure, it's extremely easy to do. So basically, we know that, you know, with this we can find out D easily. So basically, you know, 4D is actually equal to 1 because we minus 3 on both sides, and D equal to 1/4. And given this, then you can plug this back. It's extremely easy to do. So basically, so these are the 3 extra number, 3 arithmetic mean between 3 and 4. So given 1/4, so this is actually 3 and 1/4, and this is 3 and 1/2. This is actually 3 and 3/4. So that's the answer. And let's trying to do this problem. And sometimes when you given a more generic problem, given the geometric mean of two number, you know, x and y, so proves that each term in geometric sequence is geometric mean of the nearest neighbor. So basically, nearest neighbor, basically we make a generic assumption that, you know, we can say that it's an. An's nearest neighbor is an minus 1 and the an plus 1. So basically, we kind of use a generic form of what we can do is this. So an. So basically, you know, an is a1 multiply r to the n minus 1. So basically, you know, an plus 1 is just multiply 1 extra r. It's a1 to the nth. A minus 1 is just scaled down by r. It's going to be a1 to the r n minus 2. Does this make sense to use? Just hope, you know, a lot of things is just algebra, really just replacing the number and the position and you will get it. So basically, you know, what we need to prove, it's a geometric mean of nearest neighbor. So geometric mean of the nearest neighbor, it's literally, so nearest neighbor are those two number, is a1 and r to the n minus 1 multiply a1 r to the n, and you have to take a square root. So basically that's going to be, this is a1 square because I have two of those. Then R, if we add the index 2n, sorry, this is not -1, this is -2 because I had to do this. So -2 squared. So we notice that, you know, the index of those three number are all like even number. Basically, this is just a1, and this is R to the n minus 1. And this is exactly the formula of the an itself, so equal to an. So basically, this is, you know, proved that, you know, an minus 1, an plus 1, the geometric average, if you expand it out, is actually equal to the, you know, each term equal to that term. So each term in the geometric sequence is the average, geometric average of its neighbor. So let's try to see insert to geometric mean between. So when you see insert, just follow the formula. So basically, you know, between 3 and 4, so A1 equal to 3, then A2, because I have to insert 2 extra, A2 equal to 3R, and A3 equal to 3R square, and A4 equal to 3R cube, and is also equal to 4, because, you know, they are, we have two number at both end in the site. We need to stuff in two geometric mean, so it has to be arranged this way. So given this structure, so we know that, you know, 3R to the cube equal to 4, and then R cube equal to like 4 over 3, and R equals to cubical root of 4/3. So that's the common ratio. So basically, you know, we just have to figure out those number, and then basically we just multiply. So A2 going to be 3 multiply, and so this is just, you know, we have to use the radical, simplify the radical, and so basically we can put this inside it. Put this inside the radical, we will just equals to like still cube root, and this going to be 3 to the cube. So basically 3 multiply 3 multiply 3. So here still like 4. And here, so this disappear after I stuff this inside the cubical root. Then I got 3 on the bottom, and this 3 I can cancel this out. So basically there's nothing on the bottom, it's just 1. When you cancel out, it's not 0, it's 1. So it's 4 multiply, and those are the powers. This is 4 is 2 to the second. Second is not big enough to extract out the integer like root. So basically it will be combined with yin. So 4 multiply 9 equals 36. So basically the second number is 36 cube root. Then the third number, basically, you know, we will trying to put in like, so basically, you know, we can multiply upon this to get a false number because we already have an intermediate result. So this cubical root of 36 multiply cubical root of 4/3. Basically, this is just, we can cancel because those are always in the cubic root, I can make a big cubic root, 3 multiply 12, and multiply 4 over 3, and 3 is gone. And then we got like 4 multiply 12. 4 multiply 12, we will extract the, like you expressing the cube, express in the index form. So basically, prime, we complete prime factoid. This is 2 square, multiply 3, multiply 2 square. So it's actually equal to 2 to the 4th multiply 3. So basically, so this is actually, equal to cube root of 2 to the 4th multiply 3. And so I'm going to return back to here. So basically, I have enough space. So basically, this is actually equal to, this is, you can say that it's actually, because there's 2 to the 3rd, you can extract one of the two. Then the remaining 2 will just become combined with 3. 2 multiply 3 equal to 6. So basically, that's the answer. Yeah. And so basically, we actually get those answer. So this one, let's trying to do this one. And this one is actually an infinite series. So infinite series, a lot of time, if you solve those, and just don't be scared, trying to plug in at least a few number. So let's say n equal to 0. N equal to 0, what will the starting term? And n equal to 0, this term, this addend is became like a to the zeros is just 1. And 3 to the 0 is 1. And the 5 to the 0 is 1. So basically, n equal to 0, it look like this. We can write a few terms. N equal to 1, what will look like? It's going to be 8 to the first, just 8. And 3 to the first, 3. And plus 5 to the first is just 5. And 1 n equals 2, it's going to be 8 square. And that's going to be 3 square plus 5 square. So basically, if we write out a few terms, then basically, if you can do n equal to 3, then you will actually get 8 cube and 3 cube plus 5 cube. So basically, it's an infinite series, looks like, we can, and there's no multiple relationship between the second term and the first term and the third term to the second term. But if we do this, if we split them apart, then we actually will get, is actually will equal to 1 plus 1, 3 plus 3 square plus 3 cube. So plus, and this will go all the way to infinity. And this is plus 1 plus 5 plus 5 squared plus 5 cubed plus all the way to infinity. So if you are able to write out to their steps, then things became clear. So it's actually a summation of two separate geometric series. It's an infinite series. Infinite series is extremely easy to remember. It's just, A is the leading term over the R. Let me write it as a side note. So A over 1 minus R. So there are two sequences here. There are two series here. For the top one, R equals 3/8. And A1 equal to 1. So it's actually 1 divided by 1 minus 3/8. So that's for this part. Then plus 1 over and 1 minus 5/8. So this is the way that you can get it. And here, basically it's 8/5, 1/5 plus 1/3/8, and this equal to, and divide by a fraction equal multiply its reciprocal. So basically equal to 5/8 plus 3/8. Sorry, it's 8/5, 8/3. So 8/5 plus 8/3. So basically that's going to be equal to, and this is a coprime. So basically you can just 15 and 3 multiply 24 equals, or 3 multiply 24 and 5 multiply 8 equals 40. And so it's going to be like 64 divided by 15. Yeah. So that's good enough. But if you really want to know it, it's just 4 and 4/15. No, 5/15, it's 4/15. So basically that's the answer for this one. And so this one is that what value of x does this add to 4? So basically we have 4 inside. This is obviously is a geometric infinite theory. And how do we do that? So basically, and it looks like the ratio is just r. You know, the ratio r, fixed ratio is just equal to x. So basically, you know, this is summation up to 4. So basically, you know, this is 4 and the summation is just 1. The leading term is 1 and 1 minus x. So we can find out x. This is an easy one. And the 1 equal to 4 minus 4x. And this is 1/4 equals to, not 1/4. Let me, so this goes to this side, 4x equal to, and this goes this side equal to 3, and x equal to 3/4. So that's the answer. And so there's an extra problem, and so we're trying to understand what is this meaning. So basically, can you figure out must mean what its value? So basically, it's a double sum, and so it's rotate. You know, J rotate from 1 to 4. So J and K is also from 1 to 4. And so if we really trying to expand it, and it is actually, so the K is on the outside. So we start rotating from the K. So when K is equal to 1, so if you got confused, you kind of just starting from, so when K equal to 1, then what, this is going to be just 1. So basically, you know, K equal to 1, then basically the term, the inner term looks like sigma J equal to 1 to 4. And K is already 1, it's just J. So this is, then basically, so right now K equals 2. K equal to 2, basically, you know, 2 is here, so you can replace the 2 here. So it's sigma J equal to 1 to 4 and 2J. And then K equal to 3, you're going to be like sigma J equal to 1 to 4 and 3J, because K became 3 and you replace, plug in here, K equal to 4 and so it's sigma J equal to 1 to 4 and 4J. So basically, you know, these are the terms. And then right now I can expand it. So this one basically, you know, if you really expand it, it's going to be from 1 to 4. So basically, so for this portion, if you expand it, it's going to be like 1 plus 2 plus 3 plus 4. And then for k equal to 2, so this term basically 2j. When j equal to 1, 2 multiply 1 equal to 2. So it's just double whatever this is. So it's 2 plus 4 plus 6 plus 8. And this is 3j, so it's starting from 3 plus 6 plus 9 plus 12, and plus, 4 plus 8 plus, and 12 plus 16. And so this is just the way it's going to be arranged. And if you really do it, this is 10, this part, and this is double the 10, so it's 20. This is triple the 10, it's just 30. This is quadruple the 10, it's just 40. So if you add it together, it's just going to be 100 for this problem. And let me trying to see that. This is 4/8 and 4/12. Let me try to extract the problem and see if we can. Okay, so let's try to do this one. $24, 8. Yeah, shows that equation 24(1) yield the polynomial factorization. Yeah, 24(1). Let me see what is 24(1). Oh, equation. Yeah, so 24(1) is this one. And so basically, shows that, this prime factorization is, we actually just starting from here. So if we have assume if we have a geometric sequence is 1 plus x plus, and plus all the way to x k minus 1, because it's a geometric sequence, we use the formula. We can use this formula. So we use this as a formula. So this is the partial sum of geometric sequence equal to 1 minus r. And here we replace r because x is the r. So 1 minus x. And then the top basically is just 1 minus, and so this is the last term, it's just x k. So that's actually is the, and then we will change the, we will swap the, basically we multiply -1 both numerator and denominator. We actually will got x to the k minus 1 is divided by x minus 1. So this basically, is actually is equal to this. Then we just multiply x minus 1 on both sides. So this is we basically multiply x minus 1 both 1 and 2 here to mean this part. So basically you will get you can reorder this. You can also reorder this, reorder the 1 into, so basically we will got xk minus 1 and equal to x minus 1. Because I can reorder this, so it's actually xk k minus 1 plus x k minus 2 and add all the way to x and plus 1. So that's the way to solve this problem. And let's try to do this problem, the last problem. And it's great that you guys are working on the problem. It's really important that you do certain practice to keep you sharp. Otherwise, the math, if you don't really practice yourself, it's going to be very hard in the future to really master it, because you actually will be competing with a lot of other smart kids. And okay, so yeah, this is how many grain would she have if she had asked for 1, 2, 3 rather than this. This is just a arithmetic sequence. So basically, you know, let's check the background of this problem. So I think 2, 6 is on this problem. It's just showing, how much differ so a geometric sequence. A fable says that a wise woman asked or solved a king's dire problem as king asked. The king said she could have anything she wanted in return. She demurely asked only for a chessboard with 1 grain of wheat, the first square, and the second, 2 on the second, 4 on the third, 8 on the fourth, and so on. So basically, this basically is a geometric sequence, and it's going to be a huge number. So basically, the ratio is 2. So basically, the bottom going to be 1 minus r. So 1 minus 2, and the top going to be 1 minus, the last term basically is 2 to the 63, and then multiply 2 again. So it's 2 to the 64. And if we multiply both top and bottom, we will got the sum is equal to 2 to the 64 minus 1. And this is a whole lot of big numbers. This is a big number, as big as like about between 1 to 2,000 years of grain production the whole world can produce. So, but if she is really being modest, she should ask for the arithmetic sequence, and basically that will be really little. So it's actually, we have, it's big chessboard, you have 64 squares. So basically, Sn for the arithmetic is equal to like 64 is the number of the numbers. And this is the leading number plus the ending number is basically 64 and divided by 4, divided by 2. So this is the average of it. So this is basically 65 multiply, this is 32. So basically that's whatever the number produce. It's going to be a small number. Maybe it's not even enough rice to fill your belly in for 1 meal. Okay, so we kind of get through the last time's problem. Let's keep on going for today's topic. And today's topic, we are going to go through the the polynomial, and polynomial. So we have been able to solve the first degree polynomial and the second degree polynomial. Second degree polynomial is we actually has a formula, so it's easy. But how about higher power of the like polynomial? And it may not be that easy. First, we have to understand what is a polynomial. And so polynomial are the functions with this form. So, this is the leading term, an and x to the nth plus n minus 1 to the n multiply x to the n minus 1 and plus all the way to a0. So this is, the leading term. Except for the leading term, everything can be 0. The coefficient could be 0. So if you do a polynomial, the leading term must be non-zero. And let's check some examples. So this one is a polynomial. It is, 3 third degree here. So the leading term decide the whole polynomial's index. So it's a third degree polynomial. It's fine to miss a square term. There's no square term here. And this one is actually also okay because it has a radical coefficient, but every number is 4, 3, 2, 1, and the x to the 0th power. And these three are all legit ones. And this is not. This is a fraction function, and fraction function simply cannot decide its degree and things. So basically, it's not a polynomial. Portion of it, on denominator, it's a polynomial, on the numerator, it's a polynomial, but combined together, it's not. And this one is not a polynomial because it don't have a polynomial has to get an integer like degree. So basically, and so this one, because if you really look at it, it's actually x to the 1/2. 1/2 is not an integer. It is not an integer degree. So basically, it's not a polynomial. And this one is not. And this one is not. And this one, because you have a negative ones, basically x to the negative 1, it has to be like positive integer. And this one, it's not a trigonometry, has nothing to do with it. So, so polynomial, what are we going to do with the polynomial? And polynomial, we're going to have know how to do the multiplication and the division. And we also going to be able to learn the synthetic division. So I think, we have a lot of content today. We also going to solve the higher degree. So we have a lot of content going to be taught today. And so stay with us on the right. And first is multiplication. Multiplication, if it is a binomial, multiplied binomial, we know we have a FOIL, FOIL. And but how about even higher degree? And with given more higher degree, basically, we use this type of the multiplication. We kind of line up the each expression by a descending degree. And on the top, then when we multiply, the first line is this number multiply the whole polynomial. And when you distribute this number into those three terms, you record down here. And number 2 basically is this term, -3, distributing to the top 1. And this is x squared distributing to the top 1. So basically, when we add it up, the advantage of it, it's like has a descending, always has a descending like degree. You can line up, so you're adding the terms of the vertically aligned one, you're able to do it fairly conveniently. Then we actually going to do the division. And we're going to introduce the polynomial division. And polynomial division basically is that, for example, I have a polynomial and divided another polynomial. How we going to do it is just still kind of arrange it in the descending degree. And then, for example, I have a quadratic term here and a cubic term here. So the quotient is like linear. So the quotient is linear. So you multiply them, you actually will get a, I will get a cubic term here. Then I can minus it to really cancel them out. So with the goal of canceling the highest degree term in the first as our priority, you can begin to write down the like polynomial quotient, and then there's a remainder. So that's the way. And so the polynomial division, when you divide, so f function f divided by g is actually equal to q. Q is, for example, in this case, f is this quadratic expression x squared plus 2x plus 1 and divided by g. G is a, oh, sorry, the divisor, the dividend is f in the middle is x cubed plus 2x squared plus 4x plus 4, and gx is the one being divided. This one is the one is dividing into this one. G is the divisor which divide into the dividend. Then x plus 1 is the quotient. Then there's a remainder. And the remainder always has a degree less than the divisor. So that's the, and because the problem are actually not very easy, and we're going to do a lot of those. So it's also going to, we also going to introduce a synthetic division. So we're going to introduce the synthetic division, and so there's a one style of the division is quite difficult. If we divide in this way, so the first question, when going to use the synthetic division. So this one we have to use a normal style. This is a normal style division because it's the divisor is a quadratic term. And but in special case, when you divide by a linear, like by a linear polynomial, if you have a polynomial, is a high degree polynomial divided by a linear polynomial, you actually can use the synthetic division. Synthetic division basically will use the a simplified format to deal with the division. So you actually will write down much easier. So let's do this example. So when you divide this by this, and synthetic division has one restriction that the divisor has to be monic. So this is not monic. So monic means that x, so the x term has just number 1 as coefficient. So basically, if we do some manipulation, we can change this into monic. We do this by dividing both numerator and denominator by 2. So basically, you can write it into x plus 1/2, because this part is divided by 2, and this part divided by 2 is just 4x, 4 minus 6x cubed plus x plus 1/2. So given this, and synthetic division just take the coefficient of all the polynomials and line them up. So it's 4 minus 6 plus 1 plus 1/2. And divide by, so the divisor going to be here. And because it's 2x plus 1/2 is x plus 1/2 is actually equal to x minus negative 1/2. So we actually, when you use synthetic division, always use the minus form to plug here. So minus 1/2. So basically, then the next step, you drop down the first number here. 4 multiplies this going to be 4 divided by 2. And also take the negative sign is going to be -2. And then basically we add them up. It's going to be -8. Add them up vertically and put it here. Then negative going to be positive, and 8 divided by 2 equal to 4. So this is 1 plus 4 equal to 5. So basically we will get a -5/2. So yeah. So basically, we are able to sum them up here, and here we're going to get -2. So that's the way that we are able to divide it up. And let me check my division. Yeah. Oh, I didn't do it. Yeah, I missed one term. Sorry. I did it right. I was wondering why it's wrong, because synthetic division, you actually have to include it always had to descending order. So I missed one of the x term. It's x, so it's 4. Let me do it again. So it's actually 4. There's a 0x squared. So basically 4 minus x plus 1, not plus 1. And so this is plus 0, because 0 squared need to be squeezed here, and plus x plus 1/2, and then divide by -1/2. Then this is a form, multiply this going to be -2. This is -8. And then this is going to be plus 4. And 0 plus 4 equal to 4. And 4 multiply negative 2 going to be equal to divide by 2. And negative. So this is 1. And synthetic, there's no variable. You just use the, so it's going to be -2. And this is going to be -1. -1, then going to be 1/2. So remainder going to be 1. So remainder going to be 1. And that is the, so use the synthetic division. We will get this. And so the quotient going to be 4x squared, not x squared, 4x. When you divide the linear, it's going to be x cubed, then minus 8x squared plus 4x minus 1. And then because we scale everything down by 2, so we're going to be actually is this going to be have scale up again. is 2 over 2x plus 1. So basically that's the, so this is the quotient, this is the remainder. So that's the remainder will be this. So this is the way to do the synthetic and the synthetic. So let me do one more. So basically, you know, you kind of get used to it because things synthetic division is a key skill in mastering these tricks. And with the higher power polynomial, so synthetic division is a required skill, and you just have to practice it. So try to do a lot of practice. So let me trying to do this one. First, we have to make sure we are not skipping any orders or any turns. If we skip one turn, we just have to backfill a 0 turn. So here, 4 to 5, it's nothing missing. It's just, you know, descending order perfectly. So we will going to write down the coefficient of this polynomial. It's 1 plus 3 plus 2 minus, this is 1, and plus 1 minus 7. And then we divide by, so x plus 3 is actually equal to x minus negative 3. So we had to use negative 3 here. And then the first term, you always copy the, and this is already monic, so you don't have to, and the previous problem, it's not monic. So basically we had to really, you know, do some adjustment to make it monic. The divisor, so the leading, so the dividend don't has to be monic, but the divisor has to be monic. And so when we divide it, so 1 multiply negative 3 equal to negative 3, and 3 plus negative 3 equals 0, and 0 multiply negative 3 equal to 0, and 2 plus 0 equal to 2, and 2 multiply negative 3 equal to negative 6. This is going to be negative 7, and 3 multiply 7 equal to 21, so plus 21 here. And this is plus 22. And this is going to be negative 66 and negative 73. So this is going to be the remainder. And so, yeah, so the divisor going to be, so the divisor, if we write it out, going to be x fourths. And 0 is just, you know, means the cubical term is 0, and plus 2x squared minus 7x plus 22. Then the remainder, so the remainder going to be negative 73. So the remainder also have some significance. So the remainder is actually, you know, will be equal to f3. F negative 3 is going to be negative 73. Yeah, so basically, you know, it's, yeah, this time I did right. So, so we're going to repeatedly using the synthetic division, and going to, because in this part, we're going to, because polynomial has a lot of contents for this chapter, I think we're trying to cover this part, 6.3, and it may, I may not, and 6.4 is actually it's just a lot of practice from the like Vieta problem. Like if I have the time, we'll cover one or two. And let's try to cover as much as we can. So yeah. So so this is a very important result. This is extremely important result that the remainder upon dividing fx by x minus a is fa. And so basically, this one is actually not too hard to prove. Basically, I can write into a quotient form. So divide by x minus a. I think it's actually x minus a multiply a, for example, gx, then plus r and x. And rx, because the remainder's degree need to be less than the divisor. Divisor's degree is 1. Degree means the power of the x, and this actually a constant term. So rx will be constant, is actually is constant. So basically we can, if it's constant, we can say that, as x minus a gx plus c is the constant because the degree is below 1, and the only possible way is constant. If it's a constant, then we can actually pick a special number. We can, so the remainder will be the constant at any x value. So if I pick x equal to a, then a minus a equal to 0. So on the left side is fa is actually equal to 0 multiply gx plus c. And this c actually will be equal to fa. So basically the remainder, so this one remainder will be fa. So that's actually quite useful. So this is a very useful result. Means that in order to evaluate fa, all we need to do is do synthetic division, and the remainder going to be fa. So this is really important. Let me just show the significance of this. This is actually significant. So basically, this is a function of this, and we are, if, for example, if we say that fx is, so this is a polynomial, it's very big number, and it's very hard to evaluate it. For example, if I have to evaluate f -3, I have to put in the number like, -3 to the third power is actually negative, yeah, I think it's 81 multiply 3, it's 243. So it's actually negative 243 plus. So basically you have to deal with very big number. I kind of just, because that 3 multiplies this is also, you know, actually happen to cancel out. So basically, but it's dealing with quite large number. But if I try to evaluate the remainder, it actually has relative small number. And if you do a synthetic division, you can evaluate this function with a much smaller number, and the result is negative 73. And negative 73, we actually can use a calculator to prove that. So basically, let's say that, if you have a calculator, let's say this is this is the popular TI-84 pop calculator if you are using one of those. And so let's clear this, also clear this. And if we, so this is x to the fifths. So x to the fifths, and plus 3 x to the fourth, and plus 2 x to the third, and minus x squared, and plus x minus 7. So basically, we want to evaluate this fraction, or this expression at number -3. So we can use second calculate, and then we can click the value, and invariant dimension. Let me clean up some statistic. Second quit, and stats, and the plots, the stats plot is on. Let me try to clear the stats plot. Let me not use the calculator. Let me just use the table to evaluate. And right now, I can use the table to evaluate. Yeah, I can use the table to evaluate it. So basically, this f -3 y1 equal to negative 170. Let me see. Second table. Yeah, negative. It's actually negative. I think I typing something wrong. So basically, at -3, it's -73. So basically, you can use the you can use this to calculate it. So that's the way that it could be. Okay. Anyway, so let's begin to try to find the root. Example. Yeah. So let's first define the rule. So the prime tool you use to find the root of the higher polynomial is synthetic division plus guessing. And then let's define how to guess. So there are a lot of rules here. And we're going to go through them very quickly. Then we will try to do several problems. And I think it takes some practice, but basically, this is just, higher power. So like a 3, 4 or 5, whatever the power. And if you hit those problems, if you have to do it, just, do it this way. And so the first we have to understand there's is that to evaluate a function's value at a point, we just need to do the synthetic division and get a remainder. And so a special case is the root. If it is a root, then the remainder is 0. So basically, you can evenly divide into it. So basically, you can find the root by trying to do synthetic division. And if you completely divide it, then it's a root. So this is the the way you find it. Then there are theoretical like result and like fundamental theorem of algebra. And this is an important theorem that take people thousands of years to figure out. But right now it's at your fingertip. It's saying that like every non-constant polynomial has at least one root. So at least one root is the minimum root. But because after it has a root, you can completely divide into it. So it can reduce 1 degree. Then the remaining one could keep applying the fundamental theorem. So if you keep applying until it became a constant, then it actually, this implies any n degree polynomial had exactly n root. And those root could be like, those root could be like integer root or imaginary root or radical root or and they also could be repeating root, like, a double root or triple root, basically, repeating at the same number. So this is but anyway, including all these scenario, like nth degree polynomial will have exact n root. That's an important result. And then the proof is fairly, if the first part is already proved, it's fairly easy, basically, exact n root, because if you already know the root, you can just divide this polynomial by the x minus root 1, then basically the quotient will have no remainder. And then the degree of the quotient is just 1 less than the original polynomial. So basically you keep applying it until it's totally factored. Then basically that's exact n roots. And then we also have an important result called like rational root theorem. A rational root theorem states that you know, if you have a polynomial that made up of all the coefficient are integers, you know, a1, an minus 1, so all the with integer coefficient, then all the rational roots are in the form of p divided by q, and pq are coprime, and then absolute value of p and absolute value of q, you know, they can evenly divide into the leading and the tail coefficient. So the p is the numerator. Numerator can evenly divide into the tail coefficient, and the q is the denominator, can evenly divide into the leading coefficient. So that's an important result. And right now the content may seem dry, but I'm going to repeatedly do several problems, just show you how to do it. Because right now we have to go through the concept and the theorem first. And this is a very important result to guess how many positive and negative number solution you have, called Descartes' rule of signs. So, we can counting the change of the sign of the coefficient to guess at most how many, positive and negative root. For example, this is fx, and we have to order the coefficient in descending order. Then basically, this is 3 to 3, no sign change. 3 to 2, no sign change. 2 to negative 3, a sign change. A negative 3 to positive 2, another sign change. And positive 2 to negative 1, another sign change. So we have 3 sign change here. So we can have at most 3 positive solution. And here, then we will re-evaluate fx with a negative x. So if you feel negative x here, so this, because it's an even, or this is an odd power, so it became negative 3. And because negative x to the 5th power is negative x to the 5th hour. So basically this became negative sign. This is positive. This became a this is also a positive because it's an even. And this is odd function, so it became negative, change the sign. And so here we just judging the sign change, negative to positive, so one sign change, and positive to negative, another sign change. And so basically, actually we have, at most 2 negative, 2, not 3, it's actually 2 negative solution. And so if also the number of the solution always, for example, they at most 3 positive, it could be just one positive solution. And if it's one positive solution, then the 2 other actually will be imaginary. And it could have 2 negative solutions, but it could have also 0 solutions, and with 2 sign change. If it's 0, then basically 2 of those actually are like complex solution. So basically, we also can use the upper bound and the lower bound, to detect the sign change and trying to find the, for example, if we like FA, for example, is positive, like FB equals to negative, that actually means that, for example, A is here and B is here. That means that if because polynomial function are always continuous, so at some point it's going to hit this, cross the 0 lines, it will produce a real root. So basically, if you have the upper bound and lower bound, and then if have a sign change, then you can trying to use a vice, trying to squeeze from both sides, trying to find the root. And a lot of computer software do that way. If you have a sign change in the function evaluation, and if the function is continuous, it will guarantee to find that root for you. And then also another important result is that radical root and the complex root come in pairs. These are the conjugate. So basically, like you can prove that, the conjugate, if a root, in an integer coefficient like polynomial, if you have a radical root, then its conjugate is also a root. Or if you have a complex root, its conjugate is also a root. Okay, so these are the function, the properties we need to go through. It's very dry right now. I know that it looks very, I'm going to do at least like several problems so that help you to get started on this. So here, find out all the root, so first thing we know that this is this is an integer coefficient. And then second, we can see, how many positive and negative root we will have. So fx this is positive, this is negative, positive, negative. So this is from positive to negative, one sign change, another sign change. So 3 sign change. And we have 3 possible positive root. And the third thing is that, the coefficient of this. So the leading coefficient is 1, the tail coefficient is 6. So basically, how many integer solution, how many rational solution. So it's in the form of PQ. And because the Q is actually 1, because the leading coefficient is 1. And so basically it's 6, 1 of the factor of the 6, and divide by 1 of the factor of the leading and so it's 1 of the factor of this. Factor of 6 is just, 1, 2, and 3, and 6, and over 1. So it's any of those are possible. So basically, given those information, how do I trying to evaluate? Then basically, the first, we will just try those numbers. So the first, obviously, try 1. 1 is easy one. 1 basically, I actually already tell 1 is a solution, because if I test 1 square is just 1 minus 6 and plus 11 minus 12. So the positive terms is 12, a negative term is negative 12. So 1 is a solution. So then 1 is solution. So if 1 is solution, we can just use the the synthetic division. So and let's just verify there are no missing term. If we have no missing term, it's just 1 minus 6 plus 11 minus 6. Then because 1 is a solution, so it's actually you are dividing by x minus 1. So 1 will be here. And 1, this we just drop here. 1 multiply 1 equal to 1. And this is going to be negative 5. And this is going to be negative 5. This is going to be 6. 1 multiply 6 equal to 6. And negative 6 plus 6 equals 0. So basically, actually equally dividing to it. So so basically, the first solution is x equal to 0. Then this is just remaining. I can keep dividing into it. So everything still hold here. looks like, this is basically quadratic. This is quadratic. I can't even factor it directly. I can factor it. The other two is actually x minus 3 and x minus, or x minus 2 and x minus 3, because -2 and -3 multiply up to 6. And -2 plus -3 is -5. So basically it works. So basically, if we complete factor it, we actually get a complete factorization of the whole thing. And it's actually, the three solution is x1 equal to 1, x2 equals 2, and x3 equal to 3. So that's the way for this solution. Let me do a few more. And it's not going to be very easy. You possibly have to review the video because I'm saving the video. I'm going to post it. And there are also numerous videos on other internet platforms. So you can try to just search for the synthetic division and like high power, how to solve the high power equations and polynomial equations. So find all the root. And first we find that it's actually, all integer, all descending. So there's no missing terms. So we will write it here, 2, -5, and 4, and a -1. So the first, it's all integer. So the second is that there are very few integer solutions. So integer solution is in the form of the P and the Q, because P is -1. And also we saw 3 sign change, 1, 2, 3. So basically, it has possible 3 positive one, 3 positive solution. Then the third one is at P and Q. P because that's 1, and the Q is 2. So basically, 2 basically you can use 1 or 2. So basically, it has positive solution. It could, if there's a rational solution, it could be only 1 or 1/2. Only those two possible. Because using the prime factorization and the prime combination, only those two conditions. And then let's try to plug in 1. Plugging 1 is extremely easy. And plugging 1 is just 2 minus 5 plus 6 and minus 1. So plus 4 minus 1. So it looks like it's going to add up because those add up to be 0. So basically, 1 is a like factor. 1 is a solution. So basically, we will use 1, and 1 multiplied 2 equals 2. And this add together going to be -3. And that's -3 and going to be just a positive 1. And 1 multiply 1 equal positive 1, and adding them together equals 0. So that's actually fine. So basically, the remaining one is actually, it looks like the other 1/2 is also another solution. So we can keep factoring it. And so 2 multiply 1/2 is just 1. And this is -2. And this is actually -1, so it's 0. So basically, this just means that this is x minus 1. This one means that it's just, x minus 1/2. If x minus 1/2, you actually can multiply both two numbers. You can get 2 minus 1. And then the last is that So here basically it's just meaning that x minus 1/2 multiply 2x minus 2. So basically you can extract this 2 out, it became x minus 1, and the extracted to multiply up here, it's just 2x minus 1. So basically, x minus 1. So it is a double root plus another fraction root. So basically, we are able to use the guessing to really figure out all those. Yeah, for example, this one we still going to do it, and there's no gap in the coefficient. Sign change once, twice, 3, and 4. So it has all positive root because it has up to 4 positive roots, and it actually has 0, negative root. How to find this negative root? It's just f negative x equal to negative x to the 4th minus 10 and negative x third plus 35 negative x square minus 50 negative x plus 24, and this actually equal to x to the 4th, and there's an extra negative here will be neutralized with this, so it's plus 10x squared, and this going to be plus 25x squared. And this is negative going to positive plus 50x plus 24. And this for fx has no sign change. That means that f negative x has at most 0, at most has 0 negative solution. So basically, so it looks like we see that this has 0 negative or positive. Then we will trying to evaluate it. And so this is a high power, and let's try to see if 1 will work or not. 1 plus 24 equals 25. 25 plus, so this is 60. Positive part is 60, negative part is also 60. So 1 is actually one of the solution. So we can use like 1 minus 10 plus 20 or plus 35 minus 50 plus 24. So we're going to do this problem by, we know that 1 is a solution. So 1 multiply 1 equal to 1 and negative 9 plus together. Then this negative 9 equal to negative 9. This is plus 26. This is plus 26. This is negative 24 and negative 24. So basically this is 0. So basically, this looks good. And then we will try to find an extra solution. Here it has 3 sign change, so it still has 3 possible positive root. And 3 positive root, we can try to put in numbers, and we can try to test 1. Obviously 1 do not work. And so we can try to test 2 because the last number is actually 2 cube multiply 3. So it could have 1 2, and the leading number is 1, so all over 1. So basically, I wouldn't just use all over 1 because it's just redundant. So basically, 1, 2, 3, and 4, and 8, and 12, and 24. These are all possible solutions, basically. And so we will trying to, we know 1 is not, then we will try 2. Try 2, we kind of just use the synthetic division, and 1 multiplied 2 equals 2. This is going to be -7. 2 multiplied this is -14. And this is going to be plus 12. And this going to be 24. This is going to be 0. It's also, so 2 is also one of the solution. And the remaining is actually, looks like it's 3 and 4. So basically, if you do the 3, you can also do it. So this remainder is 0. X minus 4 is one of the, or x minus 3 is one of the. Then the last is x minus 4. So basically, we complete factor it. So this is the only, because this whole function equals x minus 1 multiply x minus 2 multiply x minus 3 multiply x minus 4. So this one, all the root is 1, 2, 3, 4. I think let me do the let me try to find, to do this. I'm trying to find this root and start with x equal to 1. Start x equal to 1, then I find this equals f1 equals 10. f1 equals to 10. So f0 is actually equal to 12, negative 12. And f1 is actually equal to 10. So, if you draw the function, at some point equals to -12, and f1 is here is actually 10. So it actually means that there's a solution between 0 and 1. If there's a solution between 0 and 1, it's also positive. The only possible way is, if it's a rational, it's going to be 1/2. That's the only possible way. So it actually will help me to try the guess. So let's try to use this guess to solve it. And 2x force mine. Let me use synthetic one so I don't have to. Let's check there's no gap. Yeah, it's no gap. -15 plus 15 plus 20 minus 12. And then we will get, because 1/2 is the solution we're trying to shoot for. So 2 multiply 1/2 equal to 1. And this is negative 14, and this is going to be 7, and 22, this is going to be 11. So let me, oh, I did wrong here. I did wrong here. This is negative 14. Negative 14, and it's going to be negative 7. This is going to be 8. 8 multiplied, that's 1/2 is plus 4. That's 24. And 24 multiplied 1/2 equal to 12. So those cancel out to be 0. So we did solve 1. So after solving this, and looks like, the coefficient all are even, basically this is x minus 1/2. And so basically, this is just, 2x to the third minus 14x squared plus 8x plus 24. So basically, we can try to improve this by make this is 2x minus 1. Then basically, here became like 1 -7 plus 4 plus and 12, because I'm, just scale it down by 2. So this one, we can try to count the negative, positive, like, so this is 1 sign change and 2 sign change. So basically, it could have 2 positive, at most 2 positive. And then if we do f negative x, then we actually got, let me just write down the coefficient, and this is going to be plus 15 and plus 15. Minus 20 and minus 12. And so we actually have 1 sign change. So there's a 1 negative solution. So basically, at the second step, it became a cube solution. And cube, we will trying to see that we should be able to try like 1. It has more positive solutions. So 1, 2, and 3, and 4, and 6, and 12. So we will try those numbers, and try those numbers. Usually you can use the synthetic division, and then we're trying to solve it. And this question is only asking what you should do next. So basically, I find that between those, there's a potentially have one like one root. So basically, I take advantage and find it. It's not necessary to do the remaining to solve everything. Yeah, this is another finding the root. So basically, let's see, the preference of which root. So this is if you have negative x, it's going to be x to the 4th minus x squared or cube plus 2x to the square minus 17x minus 12. So this is 1 sign change, 2 sign change, 3 sign change. And so it can have up to 3 negative and 1 positive. So this one basically, you can use those information, try to limit. This is 21, this is not 12. So you can try to use this to eliminate. And so there are 3 negative signs, so basic or solution. So you can choose like negative 1, negative 3, negative 7, and negative 21. It should have very high chance of hitting one solution. Let's just try like negative 3. So for example, just take this number randomly, and 1 plus 1 plus 2 plus 17 like minus 21. Like this is negative 3, and 1 multiply negative 3 equal to negative 3. This is negative 2. This is plus 6 plus 8, and 24. That's going to be 7. Negative 7. Negative 7 is going to 21. So that's 0. So basically, like, here we actually got another solution is that x equal to 3. X equal to -3. Then with the remaining one is that, the sign will be, if I put in 1, actually will work. So basically I can reduce to 1. Let me cross out this 1. So solution 1 actually works because if I just plug in the number, it actually matches. And so that's going to be 1 multiply 1 equal to 1. 7 multiply 1 is 7, so 0. So basically we find two roots. One of the root is actually equal to -3. X minus -3 is just +3, and x minus 1. Then the other factor is x squared minus x plus 7. So this one only, and we trying to solve this use quadratic formula. So b squared minus 4ac, this is discriminant. Discriminant is -1 squared minus 4 multiply 1 multiply 7 equal to 1 minus 27. So it's or 28. So it's actually negative. So negative, we will just, if we have asked to solve all the roots, then the remaining one, we can just use the radical root in the quadratic functions. So anyway, I think that's all for today. And so basically, like polynomial, and we haven't even really finished all those. And it's actually, polynomial has a lot of content. So especially the computation problems, they kind of just, raise up the, like, raise up the power and make it looks daunting and scary. But, given enough tool, it's not that daunting. And if you know how to deal with it. So basically, let me do a very small summary is that, really, polynomial is like, it's all the integer sequence, like power by descending. And if you are missing one, you should add the like zero coefficient. Then the division basically is able to, especially the, divide by linear, like generically the division is that the remainder will be of the lower degrees and both Q and G. So basically any factor, the remainder will be, actually not Q. The remainder's power will be less than G if you divide by G. So basically that's remainder power degree. And then we can use the synthetic division to divide, if you use just one value at linear. And then we actually has all the rules of the roots. Basically, it defines the number of the root to be exact n roots. Also define the like rational root. If there's any rational, it may not have any rational root, but if it does exist, it only has a limited space to find it, because it always in the format of P over Q, and the P is evenly divided into a 0, which is the tail term, and the Q evenly divided into the leading term X A N. So basically, with this, then we also has the sign change. So you can guess how many root appear on the positive side and the negative side, that actually could help you to focus, because to find the root, you have to use the synthetic division, and you can like conserve your energy and trying to find the high probability root in the right side first. Then basically, you're able to squeeze the vice if you find a positive and negative value, and between them there will be at least one root, and you can try to find the number and try to cater into it. Then also we have radical root and complex root coming pairs, and if I tell you one, then you always get the other one. And I think polynomial, I'm going to assign homework, then next time going to have also more of those, and plus the function. Function is actually important concept we need to cover. So I think we will further discuss more things on this topic, and also go through the function transformation, and the also function graphing, and also a whole lot of other function manipulating tricks. But anyways, this class emphasizes the synthetic division, and just trying to do a few, also trying to watch the video, and also I can recommend a few extra video, and really trying to understand how to do the synthetic division. It's quite important. Okay, I think that's all. Have a nice one, everyone.